Hi, I'm Dennis.
And I'm Lance.
Welcome to another episode of Inside the Lab. Today we brought in Rob and Chris from our engineering team. They helped design this VRTX unit that we're looking at here. Why don't you guys tell us a little bit about your role in designing this system?
Sure. My name is Rob Curtis. I was the thermal architect for the VRTX system.
And I'm Chris Peterson. I was the acoustical architect on the VRTX system back a couple of years ago. Marketing was talking about putting a very dense, high-performance blades into an environment that folks could use in an office. And the first thing we were thinking about, okay, it's going to be in an office, it has to be quiet. And so we immediately started looking at different solution spaces that could envision that. How do we lay it out? What types of features does it need to accomplish all of this in here? One of the first things we did in support of this effort was we wanted to see, kind of get an idea of the marketplace, how folks would use this. So I provided the marketing team with an iPod with different sounds of all our different servers. And we had a cardboard mock-up, and that was literally something that he took around to different folks and played different sounds, just to make sure we were on the right page. We've got different acoustical specs in the Dell server team, and we calibrated it back to, yep, this is where it needs to be.
That's very cool. So in the process of planning and designing the system, what was your team's vision for where the system would be used?
So this VRTX would be in an office space, kind of in the corner of the room. This is a little bit different environment here. We've got a table so everybody who's watching can see the product sitting in front of us. But yeah, it would be in the corner of the room. It'd be in a hallway. Kind of where your general print servers might be. Different folks can use it different ways, but with this particular design, this is around folks, around people. So we can talk over it. We can do whatever business we need to take care of, and not be impeded by its sound.
So talk about the different sound levels. I mean, normal rooms, normal conversations, and then how this plays into those levels.
Yeah, I was mentioning office spaces. So, in order to be able to design for those, we had to know something about those types of spaces. And it turns out most offices around the world are around 35 dBA ambient to somewhere around 50 dBA. It ranges quite a bit. In contrast, if you're talking about a recording studio or something like that, you're getting way down into 15 to 20 dBA. This product is not designed for a recording studio. It is for an office environment. Now, another feature of office spaces is sound quality. What I mean by sound quality is all those hums, whistles, and so forth that you might hear from an HVAC system, or you might hear people running or driving a car. You get a lot of different sounds. They take your attention and they distract you from what you're trying to do.
Right.
So sound quality was very high priority in this, and those are again hums, whistles, modulations, those sorts of things. So we just made sure our design reflected that and didn't have any of that. So it's low levels. It's this. We're running a stress load on an M620 blade right now. And with that about 50% utilized, it's running about 41 dBA if I'm at the front bystander position for ISO 7779. Meaning if I was standing on this table about 1.5 meters away, it'd be about 41 dBA. When you run this in idle, it'll drop down to about 36 dBA. So as I mentioned before, that's right in that range of the office environment, between about 35 and 50.
So our conversations are just to help me get some perspective, or about where typically.
Sure, yeah, and when we're talking here, and if we were to look on the sound level meter, you'd see our conversations range, somewhere around 55 to 65 dBA.
Okay.
So, something that's at 41, like this is right now, doesn't intrude at all.
Right.
Now, if you got into a data center, those run anywhere, starting about 60 dBA and all the way up to 90s. It's very loud, and
Right.
when you're in the 75 to 90 range, that's when I have to be getting right into Rob's ear and be yelling at him for him to hear me. So we're not talking about data centers. This is very much an office environment server. So we're very, very proud of it because, as I said, we engaged very early on. It was a couple of years ago, and then envisioned it as part of our team and part of what we do. We look at it very early on, figure out how we're going to deliver to all those challenges. With that, one of the main things, things Rob will talk to is we had engaged very closely with thermals and other teams in order to make sure that the airflow could cool all this.
Yeah, I was gonna ask, I mean, we made it quiet. How do you make it quiet and still run efficiently and cool and
Sure.
under a workload?
Yeah, so blades in general are dense products. They require a lot of airflow. Moving the airflow isn't necessarily a difficult thing. There's fans that are available in the industry that can move the amount of airflow we need to move within this package volume. Doing it quietly was the challenge.
Right.
We started out at industry standard fans, 120 millimeter, 94 millimeter, 92 millimeter fans. Didn't cut it. They're too loud. Then we moved to some custom form factor fans. Those were also too loud. They got us close, but they were still too loud. What we ended up with was the blowers within the blower module to actually get us to be able to meet the acoustic requirements. Within this blower module, there's several unique features. We optimized the size of the blower plenum, maximize that size to get the most out of the blowers. There is a sound and vibration absorbing foam within the module to help keep the noise within the module, absorb some of the vibration. Chris, any other?
Yeah, so as Rob mentioned, with the blower module, we had many choices. We've got a large library of air movers, and we work closely with a lot of different teams on that. And we went down the path of blowers for lots of different reasons. One of them is that you can deliver greater pressure, which you need in higher impedance systems. That pressure to RPM ratio is higher. Well, why is that important? It's important because acoustics scales with RPM. It's logarithmic with RPM. So if you reduce the RPM, you reduce acoustics. Another attractive feature of blowers is that they have lots of blades. If you were looking here, you'd see about, 30-some blades in there.
Yeah, it's perfect.
Yeah, what that does is it distributes the tonal energy over a great number of frequencies. In contrast to a fan, which might have 5 or 7 blades, and all that tonal energy is focused down at the middle to lower frequency range, and it can oftentimes stand out as tones. The blower module has very low tones, which, as I mentioned earlier, plays a big role for making sure the sound quality is good, doesn't distract us from what we're talking about.
Okay, so with this system being a smaller version of the M1080 and adding in the storage, did you have to make any changes internally to the mid-plane or anything like that to help with that airflow and sound quality?
Yeah, it's interesting you bring up the mid-plane. Moving the airflow, as I mentioned, was not a challenge, but doing it quietly was the biggest thing. So there's several different things within the chassis that we did to maintain the low speeds on the blowers. One of those is the mid-plane. The mid-plane sits directly behind the blades, in between the blades and the fans, so it's an impedance to airflow. So we had to work really closely with the mechanical team and the electrical team to maximize the size of the holes in that mid-plane to reduce that impedance. There's several other features within the chassis as well. We have flapper doors on the blowers, so in case one of those needs to be removed, it doesn't create a short circuit of airflow from the back of the chassis. We also have saloon doors within the blade slots that block the airflow when there's a blade slot that's not populated. And between the blade and storage sides of the chassis, we did quite a bit of sealing. We don't want airflow that's coming through the storage side to leak into the blower area, because that reduces the amount of airflow that's going through the blades.
Right.
So that all of those things put together enabled us to keep the blower speeds low and again achieve our acoustic goals.
So you also mentioned earlier that this system now is running under stress. Can you tell us a little bit about what you have configuration-wise and how you're stressing it?
Sure. So right now we have two M520s and two M620s within this VRTX chassis. One of the M620s is running a 50% stress load, so the processor's about 50% utilized, or 50% of the max TDP on that part. It's a 95 watt processor in that blade.
Okay. I was going to ask, which ones we had?
Sure, yeah, so we have 95 watt processors are the ones that are being stressed.
Okay.
So I can actually turn the stress off now, and you and I will hear the blowers slow down pretty quickly. Whether or not it shows up on this video or not, you know, it's a pretty quiet box even when it's stressed, so it may not show up.
I've got a desktop that I think makes more noise.
Yeah.
Yeah.
So as it's going down to idle, I'll tell you a few more features about the acoustical design in here. We mentioned just the air moving parts, which we accomplished by quite a bit. Making sure the airflow impedance was improved, making sure we had blowers that would deliver greater pressure per RPM. But we also looked at vibration. Vibration, in addition to causing other problems, for example, the hard drives, can also generate noise. So we worked with the mechanical team to make sure that vibration would be dampened as it transmits, for example, from the hard drives or from the blowers or from the fans.
Right.
And on the blowers specifically, we were mentioning the blowers in the blower module earlier, but we also designed the way it attaches to the connector to make sure that its transmission from here out would be less. So a lot of things we did, not just from the air mover standpoint, but also from the structure itself. And I would open it up and show you, but actually it's within everything. It's integral to the chassis, so it'd be hard to see. But yeah, a lot of different elements went into creating low acoustics, delivering thermals, and high feature support.
That's very cool. Anything else you want to add?
No, I think it was a great overview, guys. I really appreciate y'all coming down and kind of giving us what went into making of the VRTX. It's been very interesting. I know our viewers will appreciate that. So.
Sure.
Yeah, let me say we have it down at idle now. This is running about at the front bystander position, about 36 dBA. The room, when I measured this earlier with the sound level meter, was about 40 dBA. So it doesn't really interact. They're about on par with each other. Office environment. So.
But when it was under load, I couldn't hear the clock that's on the wall, but I can barely make it out now. So yeah, that's pretty quiet.
Yeah, we want to thank Rob and Chris for coming in, giving us an inside look at that design process and planning. And you can find more on VRTX on Dell.com and also DellTechCenter.com. And we thank you guys for watching.
See y'all next time.